Welcome back, pre-calc students. Mrs. Fellon here. We are on lesson 3, unit 3. So we're finding all real roots. So this will kind of correspond to section 2.5 in your text if you're looking at the ebook. First, let's just talk about the difference between a rational number and an irrational number. Basically, how I think about it is a rational number is pretty much any number that we've kind of come in contact with. Most of the numbers we deal with are rational. What irrational numbers are numbers that kind of go on forever without any kind of pattern. So some specific irrational numbers are like pi. So this one's an irrational number. Why? Because it goes on, like we all know that pi is 3.1415 and then blah, blah, blah. So it goes on forever without any kind of pattern. So basically, that's kind of what we're looking for. If you can write a number, if there's a number that it's like going on forever, so it's infinite, but it has no pattern, like it doesn't repeat the same digits over and over again, then it's considered a rational number. This is considered, or irrational number, sorry. 5/3 is considered a rational number. Why? Because it can be written as a fraction. So all fractions, all whole numbers, all integers, all negatives, positives, all that kind of stuff are all rational numbers. Whole number like 7 is a rational number. 0.3, because of this repeating sign, 0.3 repeating, we know that 0.3 repeating is just the fraction 1/3. This is also a rational number. Again, because we can write it as a fraction is kind of one of the defining characteristics, but also it is a number that goes on forever with a pattern. The 1.357, this one as well, because of the bar above this, implies that we are repeating the 357, which means it does have a pattern, which implies then it is a rational number. Let's take a look at square root of 5 in our calculators. So if I did that, I got 2.23667977. You can tell that this is a number that's clearly going to go on, right? Like it's kind of to the end of our calculator here, but it has no pattern. So this is considered an irrational number. 2 plus the square root of 3. So 2 plus root 3. Let's see what that is. I get 3.732050808. Again, it's a decimal that goes on forever with no pattern. We're considering that an irrational number. All right, so what we're talking about in this little section is called the rational root theorem. And so the rational root theorem is basically where we're kind of talking about how we can figure out what the zeros are of our function without using technology, without using our calculator. So what it gets at is we're talking about the factor of a sub 0 and the factor of a sub n. So just as a reminder, a sub 0, if you remember, is your constant term. And a sub n is your leading coefficient. So what we're getting at here is if we want to figure out the roots of a problem, all we have to do is divide, look at the factors of our constant term divided by the factors of our leading coefficient. So I'll kind of show you a little bit about how this looks. It's not the easiest thing in the whole world or most useful, but it is something that we want to kind of get into. All right, so in this case, the factor of a sub 0, our a sub 0 is equal to -6, and our a sub n, which is our leading coefficient, would be, looks like 2. So what we're doing is we're listing the factors of -6 over the factors of 2. So the factors of -6 are going to be like 1 and 6. Normally I think about like putting them all kind of in a row. 1 and 6, 2 and 3, and then I think that's it. 1 and 6, 2 and 3. There's no other numbers that multiply. Factors of 2, I would get 1 and 2. So it looks like I have those values here. What we want to also kind of keep in mind is that we're going to put a plus or minus in this because we're going to look at all so these roots could be positive or negative. If we were to list all of these possible roots, I would say plus and minus. I'm going to list all of these combinations. So what you'd have to do is take each of these numbers on the top and divide it by each of the numbers on the bottom. So like 1 over 1 is 1. And I'm just going to put the plus or minus once so I don't have to rewrite it 100 times. So 1 over 1 is 1. 1 over 2 is a half. Then I go into the 2. 2 over 1 is 2. 2 over 2 is 1. I'm not going to write the 1 down again because we already have it as our list. So then I go 3 over 1, which is 3. 3 over 2, which is 1.5. Then I do 6 over 1, which is 6. And 6 over 2, which is 3, which was already included in our set. So what this is saying is if I had this polynomial, these are the possible values I could choose to figure out if like one of these is going to be a root of this problem. So why that's important is because if you didn't have a calculator and you're asked to figure out, like you can't factor this, you're going to basically do synthetic division to try to figure out how to divide this or how to factor it. Well, you don't want to have to be just guessing and checking like 100 different values. So this kind of narrows down your choices. You can say, okay, well now I'm going to try 1. Let's see if that works. I'll use synthetic division. I'll put 1 on the outside of my, that weird little bracket thing, and I'm going to see if it goes in there evenly. In other words, I'm going to see if there is a remainder of 0. If that doesn't work, I'll try a half. I'll try 2. I'll try -1, -2, 3. So I get it that there's a lot of possible choices, but at least this narrows them down. So that's what the rational root theorem is. It's kind of a useful tool, especially before we had calculators, but I wanted to show it to you anyways. All right, the factor theorem. So the factor theorem states a polynomial f of x has a factor, x minus k, if and only if, when you plug k into your equation, you get 0. So what this is meaning is if you plug k in, so plug k, in for x. And if your output is 0, this means it has a remainder of 0. So this is kind of like back to that other question we asked, is if something's a factor of a polynomial, you know that it goes in there evenly. So what we're doing here is I'm going to give you an example of how we're going to use, we call this like synthetic substitution. Basically how we're just going to plug it in. Rather than using synthetic division, I'm going to do it 2 ways, but rather than using synthetic division to see if it has a factor or using long division to see if it goes in there evenly, we can use kind of a shortcut way. All right, so the first one, it says, is x minus 2 a factor? So all I'm going to do is just solve that. I'm going to get my solution. So I get x equals 2. I'm going to plug 2 into my equation wherever I see x. So, I mean, again, not super hard. We're just kind of looking. Our goal here is to see is if when I plug in 2, do I get 0 as an answer? So let's try it. 2 cubed is 8. 8 times 2 is 16. 2 squared is 4. 4 times negative 11 is negative 44. Whoops. 17 times 2 is what? 34 minus 6. So 16 minus 6 is 10. 10 and 34 is 44. 44 minus 44 is 0. So then I would say, yes, this is a factor because when I plugged 2 in, my remainder or my output was 0. So I'm going to show you another way to do this. And so I'm going to do this with a different factor this time. I'm going to ask now, is x plus 1 a factor? Because that's, again, the kind of how what you might do up here. Pick a number at random, check to see if it's a factor. So you can plug it in like this to see if it goes in there evenly, or you can do synthetic division. So say in a process, you would get x equals -1, you'd set that equal to 0. But instead of plugging -1 in for x, which again is a fine way of doing it, another way of doing this is doing what we call synthetic substitution. So I'm going to do this synthetic division. So again, I'm just going to pick all the numbers off. I'm going to drop this 2 down. I'm going to add. I'm going to multiply. I'm going to, whoops, this is 30. And then I get -30 and I get -36. Remember, this is my remainder, right? This last digit. So since my remainder is not 0, this is not a factor. And so that's kind of how I know that is not a factor of that particular polynomial. So you can do it by plugging it in for x, or you can do it by using substitution and just looking to see if your remainder is 0. All right, grab your graphing calculators if you haven't already. Let's go ahead and enter this into our calculators. So if you need to pause me to go grab your calculator, please do so. So I'm going to go to y equals, I'm going to clear all this out, I'm going to enter that whole equation in. So 2x cubed minus 11x squared plus 17x minus 6. So another way to figure out what your zeros or your roots are to your equation is to look at your graph. My window is a little bit zoomed in, so I'm going to hit zoom 6, which gives me back out to my standard window. And there, I get a graph. So what we're going to do here is we're going to figure out what our zeros are from our calculator. So I'm just going to kind of sketch a graph here, right? So this is what my graph kind of looks like. And it does something like this. So I want to find this 0, and this 0. So one way of doing that is to go into your calculators, and we've done this before, right? So we're going to go to second trace, we're going to go to 0. So I'm just going to do the left bound, right bound thing. So I'm going to go below the x-axis, above the x-axis, hit enter. I get this 0 to equal 1/2. I repeat the process. Go to my second trace. This time I'm going to move this over here above, move it below, hit enter. I get x to equal 2. And then one more time. This time I'm going to go below, and a little bit above, hit enter. I get x to equal 3. So there's another option of how you find your zeros. So whether you use the rational theorem like this one and kind of plug in numbers randomly by, making some educated guesses here, whether I give you a factor and you're just verifying whether or not it's a solution, or whether you use your calculator and find your answers. Another way of looking at it is rather than using the zero function in your calculator, you can go to your table. So one of the things you will notice if you go to your table, you can find some x-intercepts in your table. Notice that I have 2, 0 and 3, 0 as a point on my table. So I can find those two x-intercepts for sure. What that'll help me is I can find a couple x-intercepts, and then it will help me be able to divide my polynomial. You'd have to change your window or your what you're counting by to be able to find that one on your table, but either way, we should be able to figure it out. All right, it says divide this polynomial by the factors we found above until we have factored form. So once we know what factors are, we can divide this polynomial. So pick your favorite factor here. It doesn't really matter which one. So I'll start with, I'll start with 2, x equals 2. So we're going to divide until we find, we're basically going to take this and we're going to divide our polynomial. So I just picked any of the factors, and I'm going to take this polynomial here, and I'm going to use synthetic division, and I'm going to divide it. I'm going to factor it. I'm going to break it down. So drop down the 2, that's 4, that's -7, that's -14, that's 3, that's 6, this is 0. This should not be, this should not be shocking to you. Remember we already proved that those were zeros, right? So this should go in there evenly. So now what I have is, if this is my 0, the factor that produced it was x minus 2. So if I write this, we kind of did this in the last section. So if I write this as my quadratic, right, I took a cubic, I divided by a linear, and I got a quadratic. So now I'm down to that. At this stage, you can factor this quadratic, right? So now what we're doing is we're trying to factor this quadratic. You can do it by normal factoring, like AC method or whatever, or we can go ahead and do this with one of the other factors we have from above. So like if I'll take the 3 this time. So if I have x equals 3, I'm going to divide this quadratic. So I'm going to take those numbers, and I'm going to divide. So 3 times 2 is 6. I get -1. This is -3. I get 0. So now I already have the x minus 2, but now this quadratic is broken into x minus 3, because that's the factor that gave me x equals 3. And then this one is 2x minus 1. So it says, what's the linear factorization for this? Well, it's what we wrote above. Here's one factor, the other factor, the other factor. So we showed it by doing division. You could also just use your zeros up here and kind of work backwards. Like you knew that x minus 3 and x minus 2. You could have also kind of worked backwards and figured out the 0 for that one. It says real roots. So basically what I'm asking for here, remember roots means solutions. So you are solving for x. So if I set this equal to 0, I get 2. If I set this equal to 0, I get 3. And if I set this equal to 0, I should get 1/2. So those are all real numbers. Like in other words, there's no imaginary. We haven't gotten into that yet. But those are all real numbers and values that we can now find. We can now, if I asked you for your solutions, those would be our solutions. So we found the same ones by using our calculator, right? But this is how we would do it, finding, using our graph. All right, we're going to do the rest of the notes in class. This is just to kind of give you kind of a heads up about what the rational root theorem is and a little bit more practice with synthetic division and some stuff with your calculator. If you have questions, please bring them to class. I will see you next time.